All right, so this video should finish out the review here. Now we're moving on to graphing. So remember, we will graph two kinds of rose curves by hand for this test. So you need to know how many petals, and you can streamline the rose curves by knowing number of petals, how far apart they are, and whether or not you need to do petal width or not. So this is just my preference. So if you have an odd number in front of theta, that's the number of petals you're going to have. So there are 3 petals here. 5 is the length. So the furthest out the petal will reach is 5. Because there are only 3 petals, the place where the petal width is 2.5 can be a bit awkward to sketch in. So I'm not going to do petal width if it's 3 petals. I do need to know that a full circle is 2 pi. There are 3 petals. So the petals should be 2 pi over 3 apart. So really all you need to do is figure out where the tip of the first petal is, and then you can spread out the rest of these 2 pi over 3. Now, how do you know how far that is? So here's 2 pi over 3, right? It's 1, 2, 3, 4 sections, if that helps you. So you don't really have to do a bunch of math to figure out where those land, just count your sections. All right, so this is a sine graph. So I'm going to plug in just a couple of points until I get what I need. We always start by plugging in 0. So I'm not sure why my pen is being so weird. So this is 5 times the sine of 3 times 0, which is still sine of 0. That's 0. So the first point doesn't help me much if this is a sine rose curve because you start at 0, 0. But then the next point should get me out to the end. So what I want to figure out is what do I plug in here to make sine of 3 theta equal to sine of pi over 2. I can't plug in pi over 2 because then it'll be 5 times sine of 3 pi over 2. So I'm just saying, well, what does theta have to be to make 3 theta equal to pi over 2? If I divide by 3, I get pi over 6. So it's when I plug in pi over 6 that I get 5 times the sine of 3 pi over 6, which is pi over 2. That's 5 times 1. So the first petal tip will be facing pi over 6, which is right here, walking forward 1, 2, 3, 4, 5. So here's the first petal. Goes like this because I'm not worried about the width of it really. And then where does the next petal go? I'm kind of done with my table because I know that the next petal should be 2/3 away from that. So remember, that's 4 sections. So from this tip, we've got 1, 2, 3, 4. So this is where the next petal would land. And then 1, 2, 3, 4. Here's where the last petal would land. I'm going to try to trace this in the order that it would at least get done. So here, the graph would have been generated like this. Start at 0, go out to 5, come back to 0, down, out to this petal, back to 0, and then it would generate up here and then back around. The order of generation is not, like how this graph is generated, is not super important for what we're doing just graphing. But it is important for knowing, like, is the radius getting farther from the origin or closer? If you take BC calculus next year, we'll need to know what interval, what section of the graph we're on for certain sections. All right, what about 2 theta? So if the number in front of the angle is even, then you've got to double that to get your number of petals. So there are 4 petals. Like I said, I'm only testing you on 3 petals or 4 petals. So, okay, and then 3 is the length. So this is going to be a little bit smaller. If it's 4 petals, it is pretty easy to plot the petal width. So I do want to know when, I want you to accurately plot when the petal is at 3 times 1/2. So as we start our little chart here, we're plugging into 3 cosine of 2 theta. We always start by plugging in 0. 3 times cosine of 2 times 0 is still 0. 3 times cosine of 0 is 3 times 1. So we face 0 and go out 3. Cosine graphs are pretty helpful because you start out at your petal, at the length of one petal right away. And then you could plot the other 4 petals right now, just not their widths quite yet, because if there are 4 petals, you're divvying up a full circle into 4 equal parts. That means that the petals should be pi over 2 apart. That's easy to visualize here. So there's a petal at 0, there's a petal at pi over 2, and pi, and 3 pi over 2. So those are the petal tips. What about which angle are we at when they're at 1.5? So what's the nice angle that we want to plug into cosine to make cosine equal to 1/2? That's pi over 3. So again, we're back to pi over 6 for this one. It's not always pi over 6. Sometimes it's pi over 12 we've seen in the past. So you just have to look at it and do a quick little calculation here. That tells me that I should be plugging in pi over 6 because that's going to give me 3 times the cosine of 2 pi over 6, which is pi over 3. That's going to give me 3 times 1/2, which is 1.5. So face pi over 6 and go forward 1.5. Remember, all rose curves have a point at 0, 0. It doesn't matter what angle makes that happen if we're just graphing. But now I know that I can use symmetry to say, oh, well, so the other point, the other petal, the other side of this petal should be, if I'm just one sector over, forward 1.5. So here's one petal. I'm going to try to draw this the way it's generated, though. So I'm just going to keep going. So here's the middle of a petal. So 1.5 on either side of it. So this graph would generate down this way and then come up here. And then it's going to go out 1.5 this way to, to this point. And then 1.5, 1.5. So then it's going to come through 0 back up to the top and back down to 0. And it'll finish out at the last petal. If we don't have a rose curve, so if there's another number that's being added or subtracted in front of your sine or cosine function, then you've just got to kind of make a table and go through. And you should know that if you're plugging into sine, it's the non-quadrants and the pi over 6s that you need. And if you're plugging into cosine, it's the non-quadrants and the pi over 3s that you need. And we go from there. So I'm going to plug into theta, and r equals 1 plus 2 sine theta. All right, so if we plug in 0, we get 1 plus 2 times sine of 0 is 0. So face 0, go forward 1. Plug in pi over 6. 1 plus 2 times sine of pi over 6 is 1/2. 1 plus 1 is 2. Then we want pi over 2. 1 plus 2 times sine of pi over 2 is 1. So face pi over 2 and go forward 3. Then you want 5 pi over 6. 1 plus 2 times still positive 1/2. Face 5 pi over 6 and go forward 2. Then pi. 1 plus 2 times 0 is 1. Now, don't jump right to symmetry and assume this is a cardioid. For both of these, figure them out. If you don't have the patterns memorized, which I do not, for some reason, I just refuse to store any brain space for which one of these is a cardioid and which one is a lemicon with an inner loop. So I'm going to just keep plugging away until I get back to where I started. So plug in 7 pi over 6. Sine is negative 1/2 there. So 1 minus 1 is 0. Now I'm here. 7 pi over 6. So now I've got to get to the bottom of the circle, 3 pi over 2. 1 plus 2 times negative 1. 1 minus 2 is negative 1. So face 3 pi over 2, go backwards 1. So this is the inner loop. And now I have enough to stop with my table because I can say, okay, we started at this point, and it would circle around, come up here. This is a little bit wobbly here, and then we would come up to the inner loop, and I know it's going to come back down to 0 and connect back here. You can keep going with your table if you want to, but you need to do enough of the table to know whether there's an inner loop or not. So, okay. All right, and then this one, same idea. We're going to plug in to a table into 2 plus 2 cosine theta. Always start with 0. 2 plus 2 times 1 is 4. So face 0, go 1, 2, 3, 4 forward. And then we're plugging in the pi over 3s because it's a cosine function. And cosine is 1/2 at pi over 3. So this is 2 plus 1 is 3. Now make sure you face the right angle too. I noticed on the quiz some of you switched where pi over 3 and pi over 6 were on your graph. So 1, 2, 3. And then pi over 2 is 2 plus 2 times 0. So face pi over 2, go forward 2. Then we want another pi over 3, so 2 pi over 3. Now cosine's negative 1/2 at 2 pi over 3. So this is 2 minus 1 is 1. So face 2 pi over 3, go forward 1. Then you're going to put in pi. 2 plus 2 times negative 1 is 0. Maybe at this point you realize it's a cardioid, but I'm just going to keep going. It's only a couple more points, so just keep plugging it in. 2 plus 2 times negative 1/2 is 2 minus 1. So face 4 pi over 3 and go forward 1, but we do have symmetry happening. 3 pi over 2 is 2 plus 2 times 0. Face 3 pi over 2, go forward 2. And finally, if you did 5 pi over 3, we'd be at 2 plus 2 times positive 1/2. Cosine's positive down there. So that's 3. And then if I put in 2 pi, we get the same thing as 0. So this graph generates like this. Call this a cardioid because it kind of looks like a rounded heart. So that would be that graph. All right, and then we get on to the content that we learned after our quiz. So remember, if you forget what to do in this section, at the very least, make a table and then see if that jogs your memory. So determine whether R is increasing or decreasing on each interval. And then also determine whether the graph is getting closer to or farther from the origin, or neither. And then justify your answer. Remember, this is where we say like R is greater than 0 and increasing or something like that. All right, so let's do one thing at a time. So let's plug in what we have. So theta, and we're plugging into 1 plus 2 sine theta. You don't have to make this sketch, but I like to remind myself of what angles I should be plugging in here. So I'm starting with 0, and I get 1 plus 2 times 0, which is 1. Then I'm going to do pi over 6. 1 plus 2 times 1/2 is 2. So far we're increasing. Pi over 4. 1 plus 2 times radical 2 over 2 is 1 plus radical 2. Remember, that's like 2 point something. Pi over 3 is going to give me 1 plus 2 times radical 3 over 2. 1 plus radical 3 is 2 point something, but it's bigger than that. And then pi over 2, 1 plus 2 times 1 is 3. These values are definitely increasing. So, I'm going to write R is increasing on this interval. And then what about, is the graph getting closer or farther from the origin? So R is increasing, and all of these R values are positive. R is greater than 0. Remember, if these two signs agree, so I think of increasing as positive behavior, positive is obviously positive. If these two signs match, think of that as positive velocity and positive acceleration. You're shooting off farther away from 0, 0. So R is increasing and R is greater than 0. So R, or the graph, you can either say R is getting farther or a graph is farther from 0, 0. I do have a little justify section on your test. So you need to know that this is what you have to write. It's not a full page of writing. It's not over explaining, just as efficiently as you can. R is increasing, R is positive, so farther from 0, 0. Okay, then we're on this interval from pi over 2 to pi. So pi over 2, we already plugged that in, we got 3. And then 2 pi over 3 would be 1 plus 2 times radical 3 over 2. So 1 plus radical 3 again. 3 pi over 4. Now sine's positive at all these angles, so you might realize like, oh, I'm just going to get the same things I got before. So you can save yourself a bit of computation here. 1 plus 1 is 2. And then pi, 1 plus 0 is 1. So we're going from 3 to 2 point something to 2 point something a little bit smaller to 2 to 1. So R is decreasing, and r is still greater than 0, these signs negate each other. I think of this still as velocity and acceleration. If they're acting against each other, you're slowing down. So the graph is getting closer to 0, 0. I am shortening my answers. If this were an AP exam, I would definitely write this out. This part I would keep, but I would write this out like the graph is getting closer to 0, 0. Okay, and then pi to 3 pi over 2. All right, so still plugging into the same r. We have pi from the previous problem was 1. So 7 pi over 6 is going to be 1 plus 2 times negative 1/2. 1 minus 1 is 0. And then we've got 5 pi over 4. 1 plus 2 times negative radical 2 over 2 is going to be 1 minus radical 2. When we plug in 4 pi over 3, we're going to get 1 minus radical 3. And when we plug in 3 pi over 2, we're going to get 1 minus 2 times 1. 1 minus 2 times negative 1. So we're going to get 3. So what is oh, no, wait, sorry. 1 plus. Goodness. 2 times negative 1. I knew something was wrong because we went from negatives to all of a sudden some positive. So let me try this again. 1 plus 2 times the sine of 3 pi over 2 is negative 1. 1 minus 2, negative 1. 0 to 1 to negative 0 point something to negative 0 point something a little bit further down to negative 1. So r is decreasing, but two different things are happening. From pi to 7 pi over 6, you've got positive r values until you hit 0, and then you've got negative r values. So there are two different things that are happening here. So r is decreasing, and r is greater than 0 on pi to 7 pi over 6. So that means that decreasing, negative, coupled with a positive, the graph is getting closer to 0, 0 on that section. And then r is still decreasing because it's getting more and more negative. But then down here, r is less than 0. So on 7 pi over 6, where we picked up to 3 pi over 2, that means that the graph is getting farther from 0, 0. I should say 7 pi over 6 right there. So two different things are happening on that interval, and this is why we don't just plug in the first and the last. Behavior can change between that, so you've got to put in all of your common angles. Okay, and then last thing here, just a couple of average rate of change problems. So find the average rate of change. Make sure you have that formula down. It's a good idea to write the formula before you dive into the math. And then use the average rate of change to approximate this function value that's been specified. So average rate of change, again, I think it's wise to write down the formula so that you don't subtract something in the wrong order. Also, when you take calculus next year, you might get credit just on a AP problem just for writing a formula down. So it's a good habit to get into. I'm going to do the work for this off to the side though. So r of pi over 4 is equal to 4 times the cosine of 2 pi over 4. So that's equal to 0. And then r of 0 is equal to 4 times the cosine of 2 times 0. So that's equal to 4. So we have 0 minus 4 over, this is just pi over 4. Negative 4 over pi over 4 is negative 16 over pi. So there's the average rate of change. It doesn't ask me to interpret, but I would say on average, R is decreasing by 16 over pi units per radian. How do we approximate? Remember, you start with the beginning value of the interval. That's your jumping off point. You're going to add to that the average rate of change, which is subtracting in this case, multiplied by the difference in the x values. So where you're plugging in minus where you started. R of 0 we just got was 4 minus 16 over pi times, this is just pi over 8, If this were not 0, you would do the subtraction here. Pi's cancel. 16 over 8 is 2. So 4 minus 2 is 2. All right. Now, I'm not going to have you, this is a no calculator test. So when we had this in homework, it was like, well, what's your error? That's another, it's a BC calculus concept. Like, how good is this approximation? So you could double check that you're in the ballpark by doing 4 times the cosine of 2 pi over 8 and seeing if it's something close to 2. But we don't have to do that for the test because I don't want to make a calculator section just for that. All right, for number 20, last problem. So again, use the formula. Plus, if you screw up your math somewhere, I will give you partial credit just for properly writing down this formula. So it's a good habit to get into. All right. What is r of pi over 3? Let's see. Let's plug that in. Just so my work's not cluttered here, I'm going to do it up here. 1 plus 2 times radical 3 over 2 is 1 plus radical 3. And then what is r of pi over 6? 1 plus 2 times 1/2. 1 plus 1 is 2. All right, so we're doing 1 plus radical 3 minus 2. And then what about this math down here? This is 2 pi over 6 minus pi over 6. So that's just pi over 6. Clean things up. 1 minus 2 is negative 1 plus radical 3 over pi over 6. And so if we instead multiply that by 6 over pi, then let's make this, I'm going to distribute negative 6 plus 6 radical 3 over pi. You could choose not to distribute as well. It doesn't matter. So there's our average rate of change. Now, is this positive or negative? If I had to interpret this, 6 radical 3 is 6 times 1 point something, so that is bigger than 6. So this difference in the numerator is positive. So this would be, on average, r is increasing by this many units per radian. All right, and then what about 5 pi over 18? So that's going to be r of pi over 6, our jumping off point, plus the average rate of change, which is this ugly thing, times the difference in the inputs, so your approximation minus your starting point. And then r of pi over 6 was a nice little 2. Let's do the subtraction here. 5 pi over 18 minus 3 pi over 18 is 2 pi over 18. Might as well make that pi over 9. These pi's are allowed to cancel. 2 plus, let's see, negative 6 plus 6 radical 3 all over 9. I'm not sure if I simplified this very far in my answer key that I posted, but we could. You can divide by 3, so might as well. Divide by 3, you get negative 2 plus 2 radical 3 all over 3. So that's our approximation for r of 5 pi over 18. And like I said, if I wanted to see if I was somewhere in the ballpark, I could plug in 5 pi over 18 into this and see what I get as a decimal, see what this is as a decimal, and compare them, see how far off I am. There is no calculator part to our test, though. So how far do I want you to simplify this? This far. I think you should have these fraction skills at this level of AP Pre-Calc.